With two small children at home, I've read more children's literature than I ever thought possible. In that classic tale by Dr. Seuss of Horton Hears a Who, the sensitive elephant with really good hearing detects sound coming from a little speck of dust. The Who's living on that speck of dust. They're rattling their tin kettles, they're banging on brass drums, they're yipping, they're yapping, all the while hollering, "We are here, we are here." And that's so altogether different activity from what we were all doing some 20 months ago or so, right? At 7 p.m., on the dot, my kids like to call it the woo time, we'd all open up our windows, we'd grab whatever was nearby, bang on it, and just scream till our voices were sore. Sure, we were saying thank you to the first responders and the essential workers who were getting us through that pandemic, but I couldn't help but think there was something more. There was something else in our voices. Like the Who's, we were desperate to be heard in our darkest hour, desperate to know the answer to that age-old question. Are we alone? Can anyone hear me? Is there anyone else out there? My research explores the possibility of life existing on other bodies of the outer solar system. In particular, I consider icy moons of Jupiter and of Saturn. Believe it or not, I didn't always know I wanted to study icy moons. In fact, I didn't even know that I wanted to be a scientist until I was almost 30, which entailed going back to school, sitting in undergrad, getting a second undergrad, sitting in 101 courses with 18-year-olds. The inspiration, that is, to study geology came from rock climbing, hanging out there on belay, looking out at the outcrops, trying to understand how they had formed. I was able to I found myself trying to figure out how the glacier carved through Yosemite Valley, creating that U-shaped valley. And so I wanted to go back to school to study everything I could about that. The idea to study other planets came to me in a movie theater. So I was sitting there watching the big Battle of Naboo scene in The Phantom Menace, and I just found myself completely distracted, despite all the action, just thinking, wait, could you have grassy plains on other planets? What would determine that? What would you need? What are the rules? So for the last 15 years or so, I've been studying the geology of icy moons of the outer solar system, the rules, trying to learn the rules, because it looks like, apparently in the beginning, it looked like some of them were actually breaking these rules. When we first started sending out missions to the outer solar system, first Pioneer, Voyager, and the Galileo mission, the expectation was that we would go to these places, and because of how cold it was way out there, that we would see only cold, dead moons. And by dead, I mean geologically dead. So like the surface of Callisto, being pockmarked with impacts from the last heavy bombardment, which was billions of years ago. So if we're seeing it today, that means basically nothing has happened since then. But what we found was anything but. Places like Io, which is the first of the Galilean moons of Jupiter, it's the most volcanically active place in the solar system, way more than Earth, spewing out volcanic gases into the atmosphere, constantly resurfacing itself with fresh lava. Then there are places like Europa, another moon of Jupiter, and my favorite. It is an icy moon. It's riddled with ridges and fractures, these crazy scallop-shaped cracks, and this amazing feature called chaos, which looks like the crust has been broken apart and then kind of like puzzle pieces has floated around on something, whether that's partial melt or more ductile ice from below. It's moved around and then that feature has been locked in. But the most exciting observation we found is that scientists have determined that on Europa and several other icy moons, there's a liquid water ocean underneath the icy shell, a global liquid ocean. in the case of Europa, which is about the size of our moon, so about a quarter of the size of Earth, there's actually twice as much water on Europa than there is on Earth. That's a lot of water. So why is that so exciting? Because water means the possibility of life. Finding water way out there in the solar system actually changed our idea of habitability. So for a long time, the conventional thinking was that there was a kind of zone, totally dictated by the proximity to your nearest star, so our sun, such that if you were too close, like Venus, it would be too hot, and there'd be no liquid water present, so no life. And if you were too cold, if you were too far, it would be too cold, so no life there. So there would be, borrowing from yet another children's classic, there would be a sweet spot, a Goldilocks zone, if you will, where the conditions were just right. So if we were going to look into other star systems, we would want to look in that very somewhat limited, narrow Goldilocks zone to search for stable liquid water and therefore life. Finding water way out at the Jovian, the Saturnian, maybe even farther, those systems, it really turns that whole notion on its head. It means that there's just a much broader range of places where we can be looking in other solar systems. And in our solar system, what that means is that if, and that's a big if there is life on some other body in our solar system, it's going to be on one of these icy moons. So you might be wondering, you might probably have some questions. All right, so I said that there was liquid water. Why is there liquid water if we expected it to be completely dead? Well, it turns out research in my lab has actually shed some light on this, and it comes down to a basic material property, say the rules, if you will, of how solids behave. So if you've ever taken a metal coat hanger, or a paper clip will do, and you've bent it back and forth, back and forth, back and forth, and you feel the junction. If you've never done this, I recommend that you do. You'll feel heat. What's happened is that you've turned your mechanical energy into heat by moving microscopic defects inside the metal, moving them back and forth, creating a kind of frictional heating inside the metal. In kind of the same way, you know that that the moon has a gravitational effect on us, right? So that's what we have, the tides that go up and down, and of course Earth affects our moon. If you now imagine these little moons traveling around Jupiter, which is gigantic, and they have these elliptical, sort of crooked orbits, that gravitational force on them as they move in different positions around is kind of doing this kind of motion, that same kind of coat hanger motion. And so just like that, in the cycle of the orbit it has, it's moving around defects in the ice, in the rock, moving them back and forth, creating heat, enough heat to, in the case of Io, cause all that volcanism, and in the case of Europa, to create and sustain a liquid ocean. So your next question might be, all right, so there's a liquid ocean. Does it have life, and how will we know? Well, just having liquid water is not, we don't know the answer to this, first off, but just having liquid water doesn't itself mean life. There are other components that are needed, so you need to have some essential chemistry. You also need to have an energy source. So it will likely take going there to learn this information. So maybe we'll want to burrow through the ice shell, taking samples, looking for biosignatures. Heck, maybe we'll even drill all the way down and send out submersibles like through the ocean, like this artist has depicted. Again, this is not real life. This is actually a kind of rather old artist depiction of what a mission to Europa might look like. But it brings up a good point. Where we would look for life would possibly be some of these vents, these black hot smokers, so to speak, on the sea floor. We don't know if Europa has them, but we know that Earth has them, and on Earth, these kinds of black hot smokers are teeming with life that doesn't need the sun, life that feeds on the water-rock reactions to get its energy. So that's where we would look. Now, would life there have the same kind of DNA, RNA base that we have here, implying a similar source, or would it have something completely different and have a different origin? We don't know. These are all excellent questions, things we'd really like to know, but we probably won't know for quite some time. In reality, a mission to go out to a probe to Europa would probably not launch until 2035 or later, take 7 years to get there, and only then begin its science. So it's our children who will be the ones that to run those missions. For now, what we do is in the lab is we prepare. So some of the things that we're working on in our lab is trying to test technology to be able to make that mission. In particular, something that we're looking at is whether fiber optic cables that would be used to communicate from the probe to the surface, if they can survive all of that faulting and cracking and exciting geology that I told you about. So that's what we're working on in the lab. But lest you think that we're ready to go ahead and have a Starbucks outpost on the surface of Europa and all of us start colonizing over there, let me go ahead and read the fine print on that travel brochure, okay? So the surface conditions are 280 degrees below 0 Fahrenheit. There's no atmosphere to breathe. It's really negligible. And if those two things didn't get you, the radiation alone would kill you within minutes. So although there might be some forms of life in the oceans on these icy moons, those are not habitable. They're habitable for that life form. They're not habitable for this life form. This life form needs Earth. This is our speck of dust, from which, for now, we continue to bang on pots and pans, and we scream out into the ether, "We are here, we are here. Is there anyone else out there?"